Greetings and welcome to Chapter 10, Section 1, where we're talking about sequences and summation notation. In this video, I'm going to walk through some slides that were prepared to go along with Blitzer's Precalculus 3rd edition book. And in these slides, we'll see some examples and some formulas, and for those of you who have the printable version of these notes, you can be taking notes as we go along, and if you don't, feel free to pause, and you're going to be seeing definitions and sort of static building block kind of information material in these blue rectangles, and then we'll also see some graphical representations of the topics that we're talking about. And very often at the end of these videos, I work some additional example problems, but I think that these slides are going to have enough problems for us that we'll just conclude at the end of these. So first, let's talk about sequences. The definition of a sequence. So first, we're talking about an infinite sequence, and we're seeing this kind of unusual notation here. And this is a function. In the truest definition of the word function, for each input value, we're only going to have one output value. So if you were to graph it, it would pass the vertical line test. So it's a function whose domain is the set of positive integers. That would be 1, 2, 3, 4, and so on. And the function values, in other words, the output values, are called terms. And the terms of the sequence. Now look, this is the sequence a sub n, and so the terms are going to be represented by a sub 1, a sub 2, a sub 3, and so on. Sometimes an infinite sequence is always going to keep going forever, thus infinite. However, there are finite sequences where we're going to stop at some particular term, and we'll call that the nth term. That's n with a little th, the nth term. And those sequences are called finite sequences. This graph here that's on the right is a graphical representation of a sequence. The x values are actually the n values that we're plugging into our function. And notice that only the integers are being worked with here. And so we have this first integer of 1 going into our function, and apparently the output, the y value, is also a 1. And then when we take a 2 and we plug it in, the output value, the y value, the a sub n value is a 1/2. 3 goes in, out comes a 1/3. 4 goes in, out comes a 1/4. You can see the pattern there, hopefully. If we were to draw a curve that passed through those points, you would end up with the graph that's on the left. And you can see there that that's also a function, but we're not going to be working with the points that are in between. We're only going to be working with these. So as a little trial problem, we'd like to write out the first 4 terms of this sequence. So I will say that a sub 1 is equal to, and then very much like a traditional function, you can take the n value of 1 and plug it into your function right over here and do a quick calculation. So negative 1/3 to the first power is equal to negative 1/3. And a sub 2 will equal negative 1/3 to the second power, which is equal to 1/9. And a sub 3 is negative 1/3 to the third power, which is negative 1/27. And a sub 4, taking a negative number like negative 1/3, raising it to an even power, so we're going to take it and raise it to the 4th power. That would equal positive 1/81. And I will let you write that into your own notes. So that's one way to create or manufacture the output values, is one at a time, taking your n value, plugging it in, and just directly generating your output value. There's another way to go about generating the terms of your sequence, and that's using a recursion formula or a recursive formula, which defines the nth term, right, there it is, n with the th, the nth term of a sequence as a function of the previous term, or sometimes the previous terms. This should really have an s with a parentheses around it. And I'll actually take just a minute and a half and show you a very famous sequence where each term is defined by the previous two terms. But in example number 1, we're being asked to write out the first 4 terms of this sequence using this recursion formula. We have to be given a starting value, and then we're being told that whatever the nth term is that we're looking for is going to equal 3 times the n minus first term, or the n minus 1th term. In other words, if we were looking for a sub 4, that would equal 3 times a sub 4 minus 1, so that would be a sub 3 minus 1. Let's go through the motions. So we know that a sub 1 is equal to 5. Let's find a sub 2. A sub 2 is equal to 3 times a sub 2 minus 1. That's this bit right here. The 2 minus 1. And then we also have to include this minus 1 at the end. Here we go. So that's equal to 3 times a sub 1 minus 1, which is equal to 3 times, if only we knew what a sub 1 is. The problem gave it to us. It's a 5. Minus 1, so we've got 15 minus 1, which is 14. So a sub 2 is equal to 14. So we're seeing how we used, in order to figure out the second term in our sequence, a sub 2, we had to utilize the preceding term, a sub 1, in order to calculate our a sub 2 value. So if you want a sub 2, you've got to know a sub 1. Now I want a sub 3, which means I'm going to need to know a sub 2, and thankfully we already calculated that. So this is going to equal 3 times, let's just go right for it, a sub 2, that's a 3 minus 1, gave us that 2, minus this 1, so that is 3 times the 14, minus 1, which equals 3 times 4 is 12, 3 times 10 is 30, 10 plus 12, 30 plus 12 is 42, minus 1 makes 41. A sub 4 equals 3 times a sub 3, the preceding term, minus 1. Alright, so this time we've got 3 times 41 minus 1, which equals 3 times 1 is 3, 3 times 40 is 120, so we've got 143, 123, minus 1 is 122. Yeah, they wanted the first 4 terms. Here's one of them, and there's the next 3. Hopefully you're getting the idea that a recursive formula requires you to know the preceding value in order to calculate the next value. The famous one is Fibonacci. The Fibonacci sequence says that the nth term is equal to the term that came before it plus the term that came before that one. So a sub n equals a sub n minus 1 plus a sub n minus 2. So the Fibonacci sequence looks like this. 1, 1, and then what's 1 plus 1? 2. And then the next term is the sum of the 2 preceding terms. So it's a 3. And then the next term is the sum of these two preceding terms. So it's a 5. And then the next term is the sum of those two terms, the 3 and the 5. So that's an 8. $13, $21, and you can keep going. Fibonacci. I'm better with numbers than I am with letters. I'm going to leave it to you to look up and spell Fibonacci. I would say it's F-I-B-O-N-A-C-C-I, Fibonacci. All right, we've made it to page 2. For those of you who have taken a statistics class, you're very familiar with factorial notation. And factorial notation tells us to find the product of all of the preceding positive integers, including the current integer all the way down through 1. And 0 factorial requires a specific part of the definition. We're going to define that to equal 1. Every once in a while that comes in handy. Not often, but sometimes. For example, 5 factorial, and that is just an exclamation point, pretty strange, is equal to 5 times 4 times 3 times 2 times 1, which is 5 times 4 is 20, 20 times 6 is 120. So that's factorial notation. I'm going to try to avoid calculating that final value as often as possible. For example here, in the numerator, there's no way I'm going to write out all 20 factors of that numerator. I'm not writing out 20 times 19 times 18 times 17 times all the way down. Forget it. But I'm going to write out a few. 20 times 19 times, and then just pretend like we got lazy here. Pretend we said, oh, I can already see my future of writing out all these numbers. I'm bailing. I don't want to do it. Let's just put a note here that says we've got to do the 18 times the 17 times the 16, right? That's what 18 factorial means. It means we're multiplying all the way down to 1. So there are actually 18 more factors in this numerator. The 18, the 17, the 16, and so on. In the denominator, we've got 2 factorial, which is 2 times 1, and then that's being multiplied by 18 times 17 times 16 times 15. So you could write them all out, the 17, 16, 15, 14, 13, all of it, and here's a 17 and a 16 and a 15 and a 14, 13, but aren't the 17s going to cancel, and the 16s are going to cancel, and the 15s are going to cancel all the way down to the 1? Absolutely. So why cancel out all of those factors individually when I can cancel out the 18 and the 17 and the 16 and the 15 all the way down, all just using one circle? Or if you like to cross them out, 1 slash knocks out all of those factors. So that is some serious canceling very rapidly. So I would actually write out my slightly expanded version of this factorial notation exactly as you're seeing it on the screen here, and then I would come in, I would cancel those out. I like to circle things that I'm canceling so that if I want to read them later, I can. If I cross them out, sometimes it makes my work illegible, so that if I'm reviewing my notes later, I've got a problem. Also here, the 20 divided by 2, that's going to reduce. It'll leave me with a 10 in the numerator and a 1 in the denominator. Don't even have to put that. In my numerator, I've got 10 times 19, which makes 190. And in the denominator, I've got 1 times 1, which makes 1. So that doesn't do anything. And we get a final answer of 190. I like it. Just double checking my work. The next expression that we're being asked to evaluate or simplify is unusual because it still has a variable in it. Or don't think of n as a variable so much as an undisclosed constant value. So we could pick an n value and plug it in there. But we're going to leave our answer in terms of n. Remember that factorial notation says the first multiple, just as it was in the previous problem, it said 20 factorial. And the first number we wrote down was a 20. This time, it's 2n plus 1 factorial. So the first number I'm going to write down is 2n plus 1. The number or the multiple or the factor that comes after it is 1 less than 2n plus 1. And how do you decrease something by 1? You subtract 1 from it. And what's 2n plus 1 minus 1? 2n. And what would be the factor that comes after that? Whatever is 1 less than 2n. Well, how do you decrease something by 1? You subtract 1 from it. From what? From the 2n. So you'd have 2n minus 1, and then 2n minus 2, 2n minus 3, 2n minus 4, for a long time. I'm going to stop there, though, because in my denominator I have 2n factorial, which would be 2n times 2n minus 1 times 2n minus 2 times 2n minus 3. All of those factors would appear in the denominator strung out. And those are going to cancel with all of those factors that would have appeared in the numerator had we written them out. I don't love the way that I've written this, so I'm going to do a little erasing and just clean this up. Now that we've talked through it a little, we're clear that the numerator would have a 2n and a 2n minus 1 and a 2n minus 2 and so on. We're clear that the denominator would have a 2n, a 2n minus 1, a 2n minus 2, and so on. So let's, in the numerator, put that factorial, that exclamation point there, and then we can just circle those two, knowing that all those factors from the numerator and denominator that are identical are going to cancel out, leaving us only with the 2n plus 1 in the numerator. If that's a little confusing, I recommend that you pick an n value. Pick an n value of 2. Pick an n value of 3. Something small. 2 or 3. You choose. Plug your n value in here. That'll allow you to turn this into an actual number, turn this into an actual number, and work through the process with some real numbers in there. And then I think maybe this canceling out that's happening here will become a little bit more clear when you've got some actual numbers, and then you can come back and look at it again in this kind of generic form. Writing out the first 4 terms of this sequence. It's a lot of multiplication. I don't know that I want to do that one. It's negative 2 times, oh, well, let's do the first 2. A sub 1 equals negative 2 times our n value is 1 minus 1 factorial. So we've got negative 2 times 0 factorial. And what is 0 factorial? On the very first page of our notes, we saw that it's defined as a 1. So here's an instance where we do need to know that 0 factorial equals 1, and our first term in our sequence is a negative 2. Then we can go for a sub 2. That's negative 2 times our n value of 2 minus 1 factorial, right? So if you want, if you're a highlighter person, and when I teach in person, I often do this because I think it's very helpful to see what components are lining up, what's getting substituted into what. So here you can see in the top right in the formula, you see that I highlighted my 2 n values in there, and then here you can see the numbers that are getting plugged in for my n values. And for that matter, those are also n values. So maybe highlighting those elements to see what it is that's actually changing as we're going through and calculating these different terms, maybe that'll be helpful to you. Alright, so we've got negative 2 times 2 minus 1 is 1 factorial. That's 1, that's just a 1. Right? It's not like 5 times 4 times 3 times 2 times 1. It's just the beginning and the ending are the same. It's 1. Okay, so this is negative 2 times 1. That's negative 2 again. Oh, let's go for a sub 3. I'm speeding up a little bit here. Negative 2 times 3 minus 1 factorial. That's negative 2 times 2 parentheses factorial. That's negative 2 times 2 times 1, which is negative 4. So you can see the things that are changing as we go through the calculation of each term. And I'm liking the look of that highlighter so that I can see what's being modified from one calculation to the next. A little more caffeine. And off we go. The next little subtopic in this section is summation notation. And what this allows us to do is to add together all of the terms of a particular sequence. And actually, sometimes it's not all the terms of a sequence. Sometimes it's just specific terms within a given sequence. So in the blue box, let's look at the notation if you're not familiar with it already. This unusual symbol in here, some of us are more familiar with it than others. That is the capital Greek letter sigma. So sometimes this is called summation notation, sometimes it's called sigma notation. Sigma. And the I value that you're seeing in this formula, and this I value right here, that's called the index of summation. N, this number, whatever the number is that's written up here, is called the upper limit of your summation. And we're being told that our I value is going to start at 1, and that's the lower limit of summation. It doesn't always start at 1. And if you look just down at the first example, example 3, you can see that our lower limit here is starting at 1, and the upper limit is starting at 5. Could I start with a lower limit of 2 or 3? Absolutely. And we'll see an example where that happens. Okay, and then here's a sub I. That's the same a sub I that we saw earlier in these notes, where I think it was actually written as a sub n maybe, and it was inside of these kind of squiggly brackets. Okay, that was defining our sequence. I told you it was a sequence, and then the terms were a sub 1, a sub 2, a sub 3, and so on, and that it was a function, right? So this is pretty much what's happening right here. And it's going to give us, as we see in example 3, some kind of a formula that we would use, that we will use to generate the terms of the sequence. What's different here is that we're then going to add the terms of that sequence. Let's give it a shot. Find the indicated sum. How many things are we going to be adding together here? We're going to have an I value of 1, and then an I value of 2, and then 3, and then 4, and then an I value of 5. So we're going to have 5 terms. There we go. Our first term, we're going to have to take a 1 and plug it into the numerator and denominator. So we're going to have 1 plus 2 factorial over 1 factorial. Plus, now let's plug in an I value of 2. So we'll have 2 plus 2 factorial over 2 factorial. And then we'll plug in the I value of 3, and then 4, and then 5. A little tedious, but that is what the question and the process require. So I will hang with you while we write that out. And it's important that the exclamation point is on the outside of the parentheses in the numerator. That way we're doing the addition that's inside the parentheses first. And Then we're applying the exclamation point, the factorial notation. I did put an equals sign over here on the left because it is equal to our original statement. And then what we're going to write down next is going to be equal to all of those fractions being added together. So in the first numerator, I need 3 factorial. That's 3 times 2 times 1 over 1 plus 4 times 3 times, times 2 times 1. I'm going to leave that just as 2 factorial because my denominator is also 2 times 1, which can be written very succinctly as 2 factorial. And then the next fraction, 5 times 4 times 3 times 2 times 1. And in the denominator, 3 times 2 times 1. Why write it out when we can just leave it in factorial notation? It's so much more compact. Plus 6 times 5 times, see where I'm going with this yet? I don't need to write all that out. 4 times 3 times 2 times 1, and in the denominator, 4 times 3 times 2 times 1, we're going to be canceling those out all in one fell swoop. 7 times 6 times 5 all the way down. That's an exclamation point. There we go. Over 5 factorial. Great. Let's do some canceling. In the first fraction, you could circle these ones. Ones don't really cancel. They just kind of go away under those circumstances. But here, the 2 and the 1 from the numerator and denominator are going to cancel out. Here, there's a 3 up here and a 2 up here and a 1 up here, which cancel with the 1s on the bottom. Here, we're canceling 4s and 3s and 2s and 1s. And lastly, 5s and 4s and 3s and 2s and 1s. A lot of canceling we get to do very quickly there. Let's write down what we have left. I see a 6 plus a 12 plus a 20 plus 30 plus 42. And then we'll see if my arithmetic fails me or not. This looks like 50 and 62. I don't want to do that one yet. Let's keep the 50. This makes 90, 92, 94, 104, 104 plus 6. I'm going with 110. You feel compelled to check my arithmetic with a little 4-function calculator. I wouldn't blame you. Arithmetic is not my favorite. Just silencing my phone so it stops beeping in the background. Alright, so there's an example of sigma notation or summation notation mixed with factorial notation. In the next example, we would like to sort of do that backwards and express the given sum using sigma notation. That's kind of fun because we get to sort of reverse engineer our own sigma notation. The index of I is the most frequently used index that I've ever seen. It's going to start at some value, it's going to end at some value, and then we'll have some kind of a formula over here. So let's try to fill in those blanks. Look over at the sum that's happening here. Are there any numbers that are changing, and are there any numbers that are staying the same? Let's look at the numbers that are changing first, because those are going to be the I values that are increasing, perhaps starting at 1 and ending at some other value. So the numbers that are changing over here are definitely the 1, there's a 2, there's a 3, there's a, presumably, a 4, 5, 6, 7, 8, 9, 10, 11, 12. So I think that we should choose an index that starts at 1 and that ends at 12. And as we march through those I values, what are we doing to them? It looks to me like we're raising them, each one of them, consistently to the 4th power. So we're taking our I value and we're raising it to the 4th power. I don't think we really need to do it in this case, but then glance over and just do sort of a little check. We're taking the number 1, plug it into here, we get 1 to the 4th power, and I see that over to the left. And then ratchet up that index value to a 2, If I take the 2, once this becomes a 2 and I plug it into here, I get 2 to the 4th power. Do we see 2 to the 4th power over here? We sure do. So I think we're on the right track with this one. I would put a box around this. I like to put boxes around my final answers, and only my final answers. In the next problem, what numbers are changing, what numbers are staying the same? Let's frame it up. We've got our sigma notation. We're starting with some sort of an index value. Remember, we've got our lower limit, our upper, and then we'll have our formula in here. What numbers are changing? Yet again, it looks like a 1 and a 2 and a 3. So I think we can safely start our index value at a 1 in our sigma notation. And then, how high does that count go? We said that there's a 1 and a 2 and a 3, and this one looks like it goes all the way up to a value of n. That's interesting. So it looks like, I'm just going to go with it because that's what the pattern suggests I'm supposed to do, is my upper limit's going to be an n. Is anything else changing? So the numerators are changing. I'm glancing into the denominator. I can see that this is 9, but it could be 9 to the 1st power. That way, I've got 9 to the 1, to the 2, to the 3, to the 4, to the 5, so all the way up to 9 to the n. So those exponents are going to be changing on us also. Let's see if we can frame up the formula on the right-hand side of our sigma. It's going to be a fraction. My numerator is changing, starting at a 1 and continuing to increment up. So I'm going to put an I there. When my I is a 1, my numerator will be a 1. That matches. Good. When my I value is a 2, this will become a 2. That matches. Good, okay. I like the way we're going with that one. And then in the denominator, there's a 9, which appears to always be in my denominator, but it's the exponent on the 9 that's changing. And what does it start with? It starts with a 1, just like our numerator started with a 1, so I'm going to put a lowercase I as my exponent on the 9. As you do more of these, you'll be able to just glance at this formula and run those first few I values through the formula, and then glance over here to the left and make sure that they're matching up with the first few terms in the sequence to confirm that you're going the right direction. I value of 1, I value of 2, I value of 3, and so on, all the way up to an I value of n. Is the n my upper limit? It sure is. I think we're done. You've seen boxes like this before. Maybe you've seen them with matrices. You've seen them with dot products, perhaps. What else? Transformations, right? Shifting, horizontal stretching or shrinking, vertical stretching or shrinking, reflections over axes, logarithms. We see tables like this where there are properties or rules that we're allowed to use. Sometimes the list is longer in some cases than in other cases. If you don't have these printable notes and this is something that you want to screenshot, I'll even move myself out of the way so you don't have to have me in your screenshot. This would be a good one to grab and print and tape into your notes maybe. The notation on the in the left-hand column I think is really good. In here we're seeing, the C value as a constant multiple times A sub I. And then over here, it looks like it's been factored out of the sigma notation, and in fact, that is what happened. So C has to be a real number. And then over to the right, we're seeing an example of it. You can see the 3 is inside the sigma notation initially, then we're seeing it outside the sigma notation. Why is it allowed to work that way? Why are we allowed to do that? With this formula right here, remember, sigma notation is generating the first, in this case, 4 terms as we go from 1 to 4, the first 4 terms of a sequence, and then sigma notation tells us to add them together. So we've got 3 times 1 squared, 3 times 2 squared, 3 times 3 squared, 3 times 4 squared. How many terms do we have? 1, 2, 3, 4. No surprise, because our index was going from 1 to 4. So we pretty much knew that we were going to have 4 terms. Do each one of those terms have a common factor? They most certainly do. There's a common factor of 3. Can we factor out a common factor from all of those terms? Absolutely. What would it look like if we did? It would look like this. The 3 gets factored out, so now it's in front of the parentheses. If you wanted to, you could distribute it back in. You would get the preceding statement, so we know that we factored correctly. And then the idea is that this 1 squared plus 2 squared plus 3 squared plus 4 squared, check it out. There it is, 1 squared plus 2 squared plus 3 squared plus 4 squared. What about the 3? It's still there. We're just going to multiply it in later. So you're able to factor the 3 out. And then we can see a conclusion written down here, which matches up with how we saw it written generally over here. So this is a really nice page, and you could go through and look at those other properties. Essentially, we've got a distributive property of sigma notation over addition and a distributive property of sigma notation over subtraction. And you've got this sort of constant multiple factoring ability. Notice that those properties up there were numbered 1 through 3, and then we're seeing a 4 down here. Even though it's written in a different color, it is following as a 4th property, which says that if inside your sigma notation you've got a number like 5 that's not interacting with the I value, right? Look at these other ones up here. Inside my sigma notation, I've got stuff with I in it. Up here, there's an I value. The index is being squared and added to itself. Here the index is being squared and multiplied by 3. Down here, there's no I value. There's no I value. So, pardon all of my scrolling. In this very first example, when I is equal to 1, can we call that the argument for the moment? When I is equal to 1, what does that equal? Well, it equals 3 times 1 squared, which is 3. When I equals 2, what does it equal? Well, it equals 3 times 2 squared, which is 12. And so on. As we go through the I values, that argument value is changing. The term of our sequence is changing in value, and then we're going to add them all up. When I is equal to 1, what does 5 equal? Still equals 5. We're not multiplying it by I. We're not raising the 5 to the I-th power. I isn't being raised to the 5 power. It's just a 5. 5th power, 5 power. What about when I is equal to 2? What does 5 equal? 5. We're not squaring it. We're not square rooting it. When I is equal to 3, 5 still equals 5. When I equals 4, it's still a 5. Those are the first 4 terms of that sequence. And sigma notation tells us to add them together. Well, you could do 5 plus 5 plus 5 plus 5, but I would rather realize that there are 4 5s. Four 5s. So we're seeing that match up. And where's the 4? There's the 4. And you've already seen the 5. There it is. Strange to use sigma notation applied to a kind of a function in here that doesn't change. The y values, right? I keep putting in I values, input values, x values, and my y values, my output values are never changing. My function never changes value. Excuse me. That would be called a constant function because it's never changing. Not changing, constant. Find the indicated sum. This is maybe one of my favorite problems to do in this section. I'll show you why. First of all, realize that we can use that same property that we were just talking about, and we can take this constant multiple of 7 and we can factor it out of the sigma statement. Let's do that right away. 7 times sigma I values are going from 1 to 6, and the argument is just an I. That's what's going to generate the terms of our sequence. Okay, so it's 7 times, and then we've got to add up a bunch of stuff, so I'm going to put it in parentheses. When I is equal to 1, I equals 1. When I is equal to 2, I equals 2. Right? As this is changing, but they're identical. So we're going to go all the way through these integers up to an I value of 6. And now we have to add all those together. Some of us have already added them together in our head. Some of us are already reaching for our calculator. But if you'll stop for just 1 second and check this out, because it's going to come in handy later. What's 1 plus 6? You say 7. What's 2 plus 5? You say 7. What's 3 plus 4? I don't have to tell you to say it. You're saying it already. It's 7 again. How many 7s do we have? 3 of them. We just bracketed them, sort of. Okay? How many terms, right? Terms are things that are being added or subtracted. How many terms are there in there? 6. Total of 6 terms. We paired them up. The 1 and the 6. The 2 and the 5. The 3 and the 4. We paired them up. How many pairs of terms are there? 3. We started with 6 terms. We had 3 pairs. How do you take a 6 and change it into a 3? You divide it by 2. And what was the value of each pair? 7. Now that's just what's happening inside these parentheses. We still have a multiple of 7 on the outside. That's this one. All right? So now we've got 7 times 3 in these parentheses times a 7 on the outside. It's all multiplication, so you can do it in whatever order you want. You could do 7 times 3 and get 21, and then do 21 times 7. I'm the kind of guy who likes to do 7 times 7 and get 49, and then multiply that by 3, which is 150 minus 3, which is 147. This idea, this process of pairing up your terms can save you a lot of work, especially if you have a professor or a teacher like me who may or may not be letting you use a fancy calculator when you're taking your test. Might force you to do some of this stuff longhand. Let's look at this weird one. Our I values, our index, it's unusual, is starting at 5 and going up to 9. So when I is equal to 5, what's your term value? What's your argument value? It's an 11. And when I equals 6, and 7, and 8, and 9, all right. Well, there are 5 11s, and I can see that because I'm counting them, right? How did I get that 5? Well, I could take my upper index minus my lower index. 9 minus 5 is, it's only 4. That's because when I did 9 minus 5, I actually took away this 5. but I need that value of 5. It's my lower index, my lower limit, so I have to put it back in. Now that's equal to 5. 9 minus 5 plus 1. That's how many 11s I have. Some of you are thinking, I heard what you just said. I see it. 9 minus 5 plus 1 is equal to 5. I see that there are 5 11s. I see that if I had not done the plus 1, I'd be in trouble because then I would only have 4 11s, which is incorrect. Why 9 minus, why the plus 1? Is it always going to work that way? It is. When you're trying to figure out how many terms there are total, you can always do upper limit minus lower limit plus 1. Are you ready to write this down? Number of terms equals upper limit minus lower limit plus 1. Let's try the next one. I'm going to give you 5 seconds, or if you want to pause it during those 5 seconds, you can, and maybe you even want to try this entire problem on your own. How many terms are there? In other words, how many 5s are we going to be adding together? That's the number of terms, upper minus lower plus 1, times, in this case, the value of each term. All the term values are the same, they're all 5s. So we have 50 5s, which equals 250. Not 1250. It says 250 in there. 54 minus 4 is 50 times 5, 250. Nice. And what about this one? There's not actually an appropriate amount of space to work this problem out, but I think we should try it. The first thing I want to do is distribute my sigma notation to this term and to this term using, I think it was the third of the properties that we talked about earlier. Let's see if I can do 2 lines of work. So my first line of work is going to say, I've got the sigma with the 27 on the top, starting my index at 4, and my argument, so to speak, is going to be the 5i. And then over here, we're going to see the sigma again with the 27 on top still starting with an I value for a lower limit of 4. And then there's going to be a 7 in here. And then in my first sigma notation right here, I can take this 5 and factor it out and bring it around and put it in front of the sigma notation. So I think I'll do that. So I've got 5 times the sum where my I value is starting at 4, it's going up to 27 still. I only have an I on the inside of that sigma now because I factored the 5 out, minus. Let's leave it in sigma notation. We'll start tearing it apart on the next line. Okay, here we go. I think I can, maybe I'm going to start way over here. We've got 5 times, and then we need to be adding, oh, let me switch colors, just because I can. Let's go to blue. So it's 5 times, and then look back over in this sort of purple color that I wrote. We need to evaluate this. In order to evaluate that, we're going to do something very similar to what we did here. All right, so what did we do here? we figured out, and if you want to go back into this and write a couple more notes, wouldn't be a bad idea. How did we figure this out? We took the number of terms that we had in here, which we said was 6 terms, and look where the 6 is. And then we said, now that's how many terms there are. And then we said, how many pairs of terms are there? And we said, well, you take the total number of terms and divide it by 2, and that's how many pairs you're going to have. So that ended up being a 3, right? Number of terms divided by 2 equals number of pairs. Ooh, I like that. I'm going to write that down. Number of terms, plural, divided by 2, and that's equal to the number of pairs. Okay, and then there was this number, the 7, inside my parentheses. Where'd that 7 come from? That was my first term plus my last term. That gave me my pair value, the value of each pair. Remember we said 1 plus 6 is 7, and 2 plus 5 is 7, and 3 plus 4 is 7. Those were the values of each pair. Leave that in there. So, first term plus last term equals pair value. Right, the value of each pair. Instead of writing pair value, you could write value of each pair. And then we multiplied those together. The 7 times 6 over 2. I'm not referring in this part of the conversation to this number 7 at all. It's not part of our conversation. All we're trying to do is figure out how to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6. We're adding up a bunch of consecutive numbers. Consecutive numbers are numbers that come one right after the other. Okay? So maybe then we could even write down, oh, let me mention one other thing. This is good for the purposes of notation. The first term in a sequence is usually referred to as a sub 1. And the last term in a sequence, that's a plus sign, is usually referred to as a sub n. Now in the problem that we were just working on, n was 6, so you could write that as a sub 6 because there were 6 terms, but generally speaking, and this looks pretty general and generic to me, generally we would say that the last term is a sub n, and that's equal to your pair value, the value of each pair. Let's take those ideas and apply them to that problem that we were talking about down here. In this summation, right, so let's come back into here. All right. The first term in that sequence is a 4. The next term in that sequence would be a 5. The next one would be a 6. And then we'd have to add dot, 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 all the way up to 25 plus 26 plus, and then it ends at 27. I think that's pretty fair. Take a second, make sure that that matches up with your understanding of that sigma notation. And then we're going to have to subtract a bunch of 7s. How many 7s are there? Look at this last sigma notation up here. How many 7s are we going to be adding together? How do we figure out how many terms there are? Upper limit minus lower limit plus 1. 27 minus 4 plus 1. That's how many 7s we're going to have. I'm going to leave it up to you to write in additional notes that this is upper minus lower plus 1, and that this equals the number of terms. If you need to write that into your notes again, do that. Okay, so that's the number of terms. I wonder how many numbers there are in here. I bet you it's the same as the total number of terms. So whatever 27 minus 4 plus 1 is, it's 24. That's how many terms there are. And these are the same terms right here. There are 24 of them. Okay. Can we finally do some arithmetic, please? This is equal to 5 times. We need how many pairs of numbers, and we're going to multiply that by the value of each pair. So it's 5 times, let's do the pair value first. So that is 31. And if you want to sneak a little note in there, right, that's the 4 plus the 27. That's the pair value times the number of pairs, which is the total number of terms divided by 2. That's the number of pairs. So you really need to make these notes as robust as possible, or as robust as you need them, right? Some of us really need that repetition. We need to see the words and then see it matching up with where the numbers are coming in and how it all lines up. So you might want to be writing this out on a separate piece of paper that's take up a half a page to write this out, because conceptually these things have to align. And hopefully you're doing some practice problems in your homework also. Okay, and then minus, over here we've got total number of terms describing how many sevens we have. So again, that was 24 terms. Let's put that in parentheses because it was in parentheses over there. That was supposed to be a 24, sorry. That's how many sevens we had. And then I'm going to start evaluating from left to right again. So I've got 31 times 12. I don't do arithmetic, so I have to quick pull up a 4-function calculator. I could do it longhand, I promise. I do still know how to do multiplication with pencil and paper. I just don't want to. 31 times 12 is equal to 372, and then I'm doing 5 times 372. I definitely wasn't going to do that by hand. I've got 1860 minus, and then I've got 24 times 7. That's a lot of sevens. That's 168. And then we need to do the 1860 minus 168, and that's 1692. Now, a more refined video, somebody would have already done all of that arithmetic, but in my videos, I like to work it out like I'm right there with you, or like we're trying to solve this problem together. I want to talk through the thought process and cover as many angles as possible on how do I make sense out of what's going on. So, while that was a little bit time consuming and a little detailed, hopefully it's beneficial to you. And as you can see, in our next section, we're going to be talking about arithmetic sequences. So we're still going to be looking at sequences and arithmetic. In order to move from one term of a sequence to another, we will be adding some consistent value. So again, that's the end of 10.1, and I look forward to seeing you in 10.2. Thanks so much.